So this video is introducing the integration technique called u-substitution, which is a very handy technique which it is used on a vast variety of different integrals that you'll be solving, or that you'll be evaluating this quarter. So I just want to start out by just showing you this is an integral that you could actually do right now without u-substitution. Normally, when we see something like this, we would just distribute the 2x, so we would say, oh, that's the same thing as the integral of 2x cubed plus 4x dx, and then we integrate just using the power rule. So that would be x to the fourth, and if I multiply 4 times out front, it will give me 4 not a 2, so I put a 1/2 out front. And then over here, we got, that has to come from x squared, and in order to get a 4 there, we need a 2 there, and then plus c. So that would be my solution without using u-substitution. Now, we could also handle this using u-substitution, and the way u-substitution works is you're looking for basically a chain rule. U-substitution is kind of integration's answer to the chain rule. So you're looking for a situation where you have a function, and the derivative of that function. So, like for example here, we notice that 2x is the derivative of x squared plus 2. So when we recognize that, we can call the original function u, so we let u equal x squared plus 2, and then we know that the derivative of u would be 2x dx. And so what we do is we do this little substitution and say, okay, that's why I call it u-substitution. We say, let's let this part here be u, and we'll let that part there be du. So you can see that right there, because of this definition, is just u, and that right there, because of this definition, is that right there. And the key with u-substitution is the new integral that we write has to be a match the old one exactly. So, and then once we do that, of course, we can just integrate it, because the idea is we're going to make something that's simpler, or maybe even possible to integrate. So what's the integral of u du? That would have to be u to the 1/2 with, I'm sorry, u squared with a 1/2 up front plus c. But of course, the original equation was in terms of x, so we're going to have to go back and substitute back in. So this would be 1/2 x squared plus 2. Squared. And I know it doesn't look exactly the same, but you can see that if we multiplied x squared plus 2 out, x plus 2 squared out, and then distribute the c, the 1/2, you would get that same expression up there. Okay, so now, of course, this would be easier to do that one, but what happens if we had the same integral almost, except for this was to the 10th power? Now you see the power of u-substitution, because I did not want, in order to do this without u-substitution, I'd have to multiply x squared plus 2 out. We'd have to go x squared plus 2 times x squared plus 2 times x squared plus 2, etc. And we get this big, huge polynomial. Then we'd have to distribute the 2x. Then we could use the power rule. That doesn't sound like fun to me. So what we're going to do is we're going to recognize that x squared plus 2 is an inside function that's going to that the chain rule will take the derivative of. So I can use that same u-substitution. So I'm going to let u equal x squared plus 2. And that means that du is equal to 2x dx. And so then we're going to rebuild our integral. So over here, I'm going to go u to the 10th du. And you can see that, once again, because of this definition, this is the same as that. So we brought the 10 with us, but we turned the x squared plus 2 into u. Likewise, because of this definition, the 2x dx is the same as that. So then we can integrate this fairly easily. That would be u to the 11th power and 1 over 11 plus c. Substitute back in and we get 1 over 11 times x squared plus 2 to the 11th power plus c. And just to impress you even further, what if we had the same problem, x squared plus 2, maybe you're getting tired of this problem, to the 10th power, but this was 8x dx. Does that ruin everything? Well, let's try it. We got u is still equal to x squared plus 2, and we got du is still equal to 2x dx, because that's what it is, right? The derivative of x squared plus 2 is 2x dx. So then when I go to rebuild my integral, I'm still going to go u to the 10th, and I'm still going to put du here. But I notice that it doesn't quite match up, right? So what we have now is we have everything. If we broke this into, 4 times 2x dx, that's what the 8 was, right? So notice now this part is taken care of with that part. This part is taken care of by that part. But we have this extra factor 4 left out. So that's no problem. We can remedy that. So I can just I can just multiply everything by 4. And now we got that part taken care of with this. So again, the key with u-substitution is the new integral you write has to match the old one exactly based on your substitutions. And so then now we can go ahead and integrate this. So that'd be u to the 11th, and that'd be 4 over 11 plus c. So that's the basic idea of u-substitution, and once you get it down, you learn that there's a lot of really helpful uses, and a lot of ways that it comes in handy. For example, if I have the integral of maybe sine over cosine dx. Well, once again, I recognize that now this you could turn this into a tangent, but notice if you turn it into a tangent, what's the integral of tangent? We don't know. So what I recognize is that if I let u equal cosine x, then du is going to be sine x dx. And we can turn our integral into du over u, which that's just natural log, isn't it? That's just the natural log of u plus c. So therefore we get natural log of cosine x plus c. Whoops, I made a mistake here, didn't I? The derivative of cosine x is actually negative sine x. Well, that's no problem. When I bring in my du here, I'm missing a negative, so I just put a little negative out front. Of course, that would turn that into negative and that into negative. Okay? Well, what if the cosine was squared on the bottom? Well, the integral of sine x dx over, or cubed, or to the 4th, or whatever. No problem. We still let u equal to cosine x. That makes du equal to sine x, negative sine x dx. And I'm going to rewrite my integral as du over u to the negative 4, but I have an extra negative, so I throw the negative in there. And over u to the 4th. I was jumping ahead of myself. And I'm going to rewrite that as the integral of negative u to the negative 4 du. And then I can integrate that to u to the negative 3. I'll put a 1/3 out front. So when I multiply by negative 3, I will get negative 1, and the power will drop to negative 4, plus c, and then of course we substitute back in, and we get 1/3 cosine x to the negative 3 plus c, otherwise known as 1/3 cosine cubed plus c. Okay, so there's some good examples of u-substitution. There's a couple more videos where I work through some more u-substitution examples, but this should get you started.